S1 was designed to combine 16 processors, each intended to match Cray-1 performance, yet the complete supercomputer was never built. Lawrence Livermore began the project in 1975 with Navy funding. The goal was more capacity for large data processing problems at lower cost. The architecture repeated one uniprocessor, then linked up to 16 through a crossbar switch, directing traffic among separate memory banks. Local caches reduced trips through that switch, while fast links moved smaller amounts of data between processors. The single processor Mark I was completed in 1978. Its multiprocessor successor, Mark IIA, was repeatedly delayed and proved unreliable. That left the ambitious architecture on paper while the working machine remained a one-processor system. The project ended in 1988, but SCALD became a third-party product. It let engineers build reusable circuit modules hierarchically and generate automated wire-wrapping instructions. An unfinished supercomputer left behind a design tool used beyond its original project. A single location ping can look harmless, yet combined with other records it may expose a sensitive pattern about a person. Neither fragment identifies the risk by itself. The mosaic effect began in intelligence analysis and national security law, where unclassified fragments were treated as pieces of a larger picture. The concern was cumulative disclosure. Separate details could collectively reveal protected information. Analysts collect, analyze, and correlate metadata, movement records, and behavior. Cross-referencing can connect an identity to activities that once seemed unrelated. The risk reaches anonymized commercial data, smart meter readings, license plate records, and government information. Removing names does not remove every identifying pattern. It also influences classification decisions and Freedom of Information Act disputes. Aggregation can help track a flu outbreak. It can also expose individuals or strategic vulnerabilities. The same analytical advantage creates a serious privacy and security trade-off for people and institutions. A physicist used timed aerial photographs, not tide gauges, to estimate Inchon's tides and seawall. That information helped make the landing possible and supported the advance toward Seoul. Inchon combined strong tidal changes with seawalls, so planners needed both water height and obstacle measurements before sending Marines ashore. Katz was a physicist and photoscientist working in Army photographic programs. Katz's photogrammetric method, meaning measurement from images, compared photographs taken at carefully timed intervals. Trigonometry then converted changing waterlines and visible features into estimated tide heights. The same analysis estimated Inchon's seawall height. Its measurements suggested the wall would not be a major obstacle, helping commanders assess the Marine landing. A 1950 amphibious command letter later reported seawall measurements close to Katz's estimates. Photographs had become measurements that planners could use to judge both access and timing. That connected what observers could see from above with decisions made at the shoreline. Earlier efficient kitchens separated the cook from children. The Munich kitchen kept the compact workflow but added a glass wall for visual contact. In the 1920s, Erna Meyer, Hannah Leroux, and Walter Schmidt designed it after criticism of Stuttgart and Frankfurt models. Those earlier kitchens prioritized efficient work but made childcare difficult. The Munich plan used about 6 square meters. Components formed one compact unit along one wall, while the square layout avoided the Frankfurt kitchen's narrow rectangle. A transparent glass partition separated cooking from living space without blocking the view. It limited odors, and adjustable cabinet shelving plus a freestanding sink supported seated work. First presented in Munich in 1928, the design preserved functional efficiency but made the kitchen more accessible to family life. The cook could work in a compact space and still watch children nearby. In 1915, Prahran kept its familiar two-platform station, while trains on its line gained Victoria's first automatic three-position signaling. Prahran had served the railway since 1860 when it opened as Greville Street. By 1867, the station carried its present name on the route later known as the Sandringham Line. On 4 October 1915, three-position signaling was provided between Richmond and Prahran. Automatic signaling meant train movements on that section were protected by signals that operated automatically rather than relying only on older arrangements. It was Victoria's first example of automatic signaling. The installation did not stop at Prahran. On 16 December 1917, three-position signaling was provided from Prahran toward Ripponlea, expanding the automatic section along the line. The protected section therefore grew beyond the original installation. Then, on 28 May 1919, the Sandringham line was electrified. The station itself remained a two-platform stop through this transition. At a 1908 Bronx glider demonstration, the launch succeeded only after a car replaced a horse as the source of motive power. Morris Park was an airfield on a former racecourse selected for open, level ground near public transportation and workshops. That convenience created the launch problem: no hill stood high enough for a glider. The Society tried a catapult, a device for assisted launching, then built a larger wooden launching structure. The solution had to replace missing elevation with external force. During the approved 1908 demonstration, earlier tow attempts used a horse. Only 2 of 6 reached the air at roughly 20 feet, then a car provided the motive power for the successful demonstration. That change made the glider's launch workable on flat ground. The field also supported aircraft construction, lectures, exhibitions, balloons, kites, and other experiments. Flight depended on infrastructure before the aircraft ever left the ground. A Mies van der Rohe building designed in 1952 began construction in 2020, and its recovered plans needed only limited code-driven changes. The design was for an unbuilt Pi Lambda Phi fraternity house in Bloomington, Indiana. Bloomington officials rejected the plans for zoning, and insufficient funding ended the project in 1957, leaving the drawings unused. Indiana University alumnus Sidney Eskenazi rediscovered the project in 2013. Sketches and floor plans came from Mies's office. Original blueprints surfaced at the Museum of Modern Art in 2014. Consultants later found additional records at the Art Institute of Chicago. Thomas Pfeiffer and partners followed the recovered design closely. Modern codes required an elevator, larger mechanical rooms and restrooms, a second emergency stair, and updated heating and ventilation. Construction on the structure began in August 2020, and the building opened in early 2022. The result was a functioning two-level university building built from an otherwise lost design. Dmitry Donskoy carried an aviary, swimming pool, sauna, and gym inside a submarine built around 20 missile silos. It was the lead ship of the Project 941 Aquila, or Typhoon-class. The Typhoon-class was designed for oversized R-39 submarine-launched ballistic missiles. Those missiles demanded a much larger structure than earlier designs. The class was intended for strategic patrols in the Arctic Ocean. Engineers used 2 main pressure hulls instead of one. Crew quarters, propulsion machinery, and equipment occupied them. Additional hulls handled control, torpedoes, and connections. The starboard hull held the recreation area. The gap between the main hulls held all 20 missile silos positioned ahead of the sail. That arrangement made the Typhoon class the largest submarines ever built. It could break through thick Arctic ice while surfacing. The design supported long patrols for its crew at sea in severe Arctic conditions.